Well, I've got one more big result to do before I call it done, and it's the Schwarz lemma, which has some important consequences and is a key tool when you start trying to demonstrate things like the Riemann mapping theorem. Anyway, it's something pretty special about analytic functions, and it's not terribly hard, so I'm going to show it to you. Any questions about anything? The Schwarz lemma is about mappings from the unit disk to itself. So I have an analytic function on the unit disk, and it maps into the unit disk, which just means that the modulus of f of z is less than 1 when the modulus of z is less than 1. That's another way to say that it maps the unit disk into the unit disk. And that has the hypothesis that f of 0 is equal to 0. That's fairly important. And the reason this is important is because of the Riemann map, you can map any simply connected domain that's not the whole complex plane to the unit disk by a one-to-one onto analytic function. And so if you know the Schwarz lemma for the disk, then it gives you information about general simply connected domains. And so that has much more far-reaching consequences than just a disk thing. Well, the conclusion of the theorem has two parts. Let's see. One is that f can't expand too fast. If this were just differentiable, there would be no such restriction. But being analytic gives us this restriction that it can't expand too fast. And so this is for all, this inequality is for all z in the unit disk. And there's a second thing. It can't have too big a derivative at the origin, which is but also wouldn't be a strict restriction if it were just merely real differentiable. And there's a second clause here that actually turns out to be very important. Furthermore, if equality were to hold in one of those things, instead of inequality, let's see, there's a clause here I have to add. If equality holds in A for some z that's not 0. Of course, equality does hold when z is 0, because f of 0 is 0. So that would just say that 0 is less than or equal to 0, which is, it's equal to 0. So it's important to say that for some z unequal to 0, or if equality holds in B, then the mapping is just a rotation. Then f of z would be equal to lambda times z, so it would be for some unimodular constant lambda. So a complex number of modulus 1. So think of that as an e to the I theta. Those are the unimodular constants on the unit disk, on the unit circle, rather. And if you multiply by e to the I theta, you're just rotating z. So, i.e., f of z is just a rotation. In that case. Questions about the statement of the theorem? Well, let's turns out to be a relatively simple thing to demonstrate. Let's define a capital F of z equal f of z over z. I want to show that that function is less than or equal to 1 if z is unequal to 0. And let's, I want to show that function is less than or equal to 1 in modulus. Then that would give me the inequality of a, and the value, this value at 0 makes a lot of sense. I'm going to give it the value f prime of 0 if z is equal to 0. And I'll show you why that makes sense. Thing to note is difference quotient at 0. That would be f of z minus f of 0 over z minus 0. Well, f of 0 is equal to 0. So that's just f of z over z. And we see that would go to f prime of 0 as z tends to 0. So that capital F is actually continuous at f is 0 at 0. We see that f of z, and of course that means it's a removable singularity. It's analytic. So by the Riemann removable singularity theorem, for example, so the aha, z equals 0 is a removable singularity. For f, for capital F. So that's an easy thing. Let's see. If you think about, now we're going to think about the maximum principle. And so if you think on the boundary is the unit circle. And f is always less than or equal to 1. So we think on the unit circle, can't think, this is invalid way of thinking. But you think, oh, on the unit circle, f of z is less than or equal to 1. And the modulus of z would be 1. So the modulus of that thing on the boundary is less than or equal to 1. And so the maximum principle would give me that that thing is less than or equal to 1 on the inside. Okay. The problem with that reasoning is f is only known to be defined and analytic inside the unit disk. So it's not even defined on the boundary. And so, of course, that's an invalid use of the maximum principle. But if you're desperate and think about it for a while, you realize, here's the idea. I'm going to do the maximum principle. I want to do it on the whole unit disk and the unit circle, but I can't. But I'm going to use the maximum principle on a disk of radius r about 0, and I'm going to let that r increase to 1. And that's going to give it to me. Okay, so let's pick any old point. Let z naught be a point in the unit disk. And let's let r be a radius with the modulus of z naught less than r less than 1. Then the max principle tells us that the modulus of f of z naught would be less than or equal to the maximum of the modulus of f on the disk of radius r about z naught, closure. And that max is equal to the max of the modulus of f let's see, since I'm not at 0, that f of z would be f of z over z when z is in the circle of radius r about z. But f mapping into the unit disk, f of z on that spot is less than or equal to 1 since it maps into the unit disk, and on the bottom the modulus of z is equal to r. This is on the circle of radius r about 0. So the great thing we get is that f of z naught is less than or equal to 1 over r. And now the moment comes when you think, that's weird. R can slide around now. R was anything bigger than the modulus of z naught. And so now we see, this is the second brilliant idea, we can let the r expand out to 1. As r goes to 1, 1 over r slides down to 1. Then 1 over r would slide down to 1. And we see that randomly chosen z naught better be less than or equal to 1. And since z naught was arbitrary, we see that modulus of f is less than or equal to 1 on the whole disk. And that gives me A and B. A and B. Check, check. Let's see, A and B, yeah, that gives me that. And now the last part is actually a consequence also of the maximum principle. Here's the second part of the statement. B was the value of f at 0. F prime of 0 was the value of capital F at 0. And so, I get both of those. Let's see, the one thing I would have to, for A, I would have to know, A gives me for z unequal to 0. But f of 0 is equal to 0, so that's true at 0, too. So that's a check. The second part of the proof is, once again, the maximum principle. If equality holds, for some z naught unequal to 0, or if equality holds in B, that that would be at z naught equals 0, then f of z would attain to be 1. Then f of z naught would be equal to 1 at z naught in the unit disk. And so it would attain its maximum. But we showed that f of z was less than or equal to 1 in modulus. So we would have a function that an analytic function that attains its maximum at a point z naught. F analytic and attaining a maximum. Let's see, max at z naught would imply that f is constant. Let's call the constant lambda. And of course, f of z naught, we know that f of z naught is equal to 1. In modulus. That would imply my lambda has modulus 1. So we're done. That's the proof. Sort of a classic application of the maximum principle. For a clever one, at least. Questions about that? Well, the first big consequence of the Schwarz lemma is you can figure out what all the one-to-one onto maps of the unit disk to itself are. And those turn out to be kind of an important thing. The big consequence of Schwarz. This is the German Schwarz. There's a French Schwarz with a TZ on the end who did the theory of distributions. It's famous. The Schwarz is in my family tree. We can determine the automorphism group of the unit disk. Those are the one-to-one onto analytic mappings. Call that aught D10. Those are the analytic maps of the unit disk to itself, which are one-to-one onto an analytic. Is given by a very specific kind of map. So it's given by the set of lambda times z minus a over 1 minus a bar z, where the modulus of lambda is 1 and a is a point inside the unit disk. Those are called the Möbius transformations. In some books. Some books call the Möbius transformations, all the linear fractional transformations would be called Möbius transformations. But these are special Möbius transformations, and sometimes the word is reserved for these. So don't be shocked if a book seems to contradict what I'm saying here. Yeah, that's an LFT, right? It looks like if I factored the lambda through the top, I'd have an AZ plus B over a CZ plus D. So that's definitely an LFT. It's just the one; those are the ones that map this unit circle to itself. Okay, I'm going to show you this. It's not hard. So here's the Y. Let's see. I'm going to use, I should show you that these things actually do map the unit disk to itself. Step 1. I'm going to write phi sub A of Z is going to be this Möbius transformation when A is a point in the unit disk. I claim that that this phi sub A maps the unit disk one-to-one onto itself. And if that's an easy thing, now that we understand linear fractional transformations, let's see, why is that true? Let's pick a point. E to the IT on the unit circle. I want to see that those points get mapped to points on the unit circle. Okay, let's think of phi sub A of E to the IT. That would be E to the IT minus A over 1 minus A bar E to the IT. And you think, that thing on the bottom kind of looks like the conjugate of the thing on the top. But the E to the IT is in the wrong place. So, we kind of played around with things like this before. If I multiply the top and the bottom by E to the minus IT, then E to the IT times E to the minus IT is 1. And so that would simplify to be, let's see, I'll leave this E to the minus IT out here in front on the top. And I'll leave, so I haven't done anything to the top, I just multiplied it through and moved it over to the left. But on the bottom, I'm going to have an E to the minus IT times 1 minus A bar. Let me move that over a little bit so it's kind of screaming at me. That thing right there, the quotient of those two things is 1. This is the conjugate of that. So these two are conjugates. The denominator is the conjugate of the numerator. And so this thing looks like E to the minus IT times the W over W bar. And those are both unimodular. So that shows me that the E to the IT gets mapped into the unit circle. These are both unimodular. And so we see that phi sub A maps the unit circle into itself. Okay, so we know that 3 points determined. I could have checked that at only 3 points. So now I'm thinking like I'm doing LFTs, which I am. I have a map here. I would pick 3 points on the unit circle. A, B, C. They all three go to A prime, B prime, C prime over here. A prime, B prime, C prime. And now the question is, what happens to the inside and the outside? That determines which part of the circle goes where. And so here we have an A. And z minus a is in the numerator. A gets mapped to 0. That's a prime. And so I don't have to use the bug test. I can use the one-point test. The one-point test tells me that the inside of this unit circle gets mapped to the inside of this unit circle, 1 to 1 and on to. So that's kind of a review about linear fractional transformations. LFTs are 1 to 1 on to, the one-point test. D1, 0 gets mapped to D1, 0, 1 to 1 and on to. So this map right here is the phi sub A map. Okay, so now how am I going to do this? So the next step is to think about the general map. Step 2. Let's suppose I got a map. Suppose F is an automorphism of the unit disk. Well, I'd like to apply the Schwarz lemma directly to F, but it might be that, well, let's see, I wanted to do, before I do step 2, I need to make an observation. Note, we have that phi a sub A of z is z minus a over 1 minus a bar z. The inverse of phi sub a, which we know how to do that. You switch the diagonal elements and let's see, I can write it like this. That's z minus a over minus a bar z plus 1. When I switch the diagonal elements and put minuses in the other spots, we see that phi sub A inverse of z is z plus a over 1 plus a bar z. Okay. So, here's my mapping of my, I'm going to get some maps of the unit disk here. I got to think. I have an F. So I'm going to put F here. And I don't know that F maps to 0. I do know it's 1 to 1 onto. So 0 gets hit. So here's 0. And let's suppose f of a equals 0. The Schwarz lemma applies to functions that map the unit disk to itself. Okay, I'm assuming this this f is 1 to 1 and on to. So I know 0 gets hit. Okay. But if I'm going to use Schwarz, I need to map the 0 to 0 by a map that maps the unit disk to itself. So I've just prepared you to, if I make this be the point 0 now, I need a map to fill in this picture. And so I'll call it phi of z equals z plus a. That's the inverse of my map I was playing around with. That maps 0 to a. Stick in z equals 0 there, you get A. And so now I've got a map that maps 0 to 0. This map here, let's call it capital F. So capital F maps the unit disk to itself, and capital F of 0 is equal to 0. So I can use Schwarz. I couldn't do that until I got it mapping 0 to 0. And all I really need is part B. B would tell me that, let's see, I need to calculate. F of z is equal to f of that phi of z. And so f prime of 0 is equal to f prime of phi of 0 times phi prime of 0. What? Okay, I'm screwing something up here. Okay, I didn't mean to do this yet. I might save this for a second. I'm going to move this down. And let's see, F is also 1 to 1 and on to, because both the maps in between are. So it's 1 to 1 and on to. So Schwarz part B is going to tell me that the derivative is less than or equal to 1. Schwarz part B tells me f prime of 0 is less than or equal to 1. But the important thing to notice here is, so this is f inverse also satisfies the same hypothesis. Also satisfies the same conditions. It's 1 to 1 on to, and f of 0 is equal to 0. So f inverse prime at 0 is also less than or equal to 1. But so the thing to note here, the inverse function theorem says that f inverse prime at 0 is equal to 1 over f prime at f inverse of 0. And that's equal to 1 over f prime of 0. So that implies that it's f prime of 0 is also greater than or equal to 1. So it's less than or equal to 1 and greater than or equal to 1. And so it's got to be equal to 1. So we conclude f prime of 0 equals 1. And then the second part of Schwarz, Schwarz part 2, now implies that f of z is a rotation. Where the modulus of lambda is equal to 1. So we're actually done. I haven't explained exactly why we're done. We're done because that means that, remember f was f of phi of z is equal to lambda z. And if I call this z here, if I call this w, w is equal to phi of z, then z would be phi inverse of w. And the inverse of that linear fractional transformation is w minus a over 1 minus a bar w. And so this would show me that f of w is equal to lambda times w minus a over 1 minus a bar w. And that's what I was telling you. I've determined all the automorphisms of the unit disk that way. So the last thing I wanted to do in the course here is sort of tell you a main ingredient in the Riemann mapping theorem. So if you were to take a second course in this material, a natural thing to do would be to prove the Riemann mapping theorem. So an important fact, the Schwarz lemma is a key ingredient in the demonstration of the Riemann mapping theorem. Any questions about that thing I just did? Okay, the Riemann mapping theorem says take any blob, it's not the whole complex plane, so it's got to be simply connected, no holes, and it's not the whole complex plane. Then the Riemann mapping theorem says there exists a one-to-one onto analytic map to the unit disk, and that maps A to 0. So the picture would be like that. And this would be one-to-one and onto analytic. Well, suppose G is another map into the unit disk. Suppose G also maps omega to the unit disk. This thing over here is the unit disk. And it's analytic. And let's suppose it also maps A to 0. I'm going to show you in 2 seconds that Schwarz implies that G prime of A is less than or equal to the in modulus than F, the Riemann map F prime at A. So a strategy for cooking up the Riemann map is to find a mapping into the unit disk and try to maximize that derivative. And that's exactly how the kind of short and sweet proof of the Riemann mapping theorem goes, with just a few facts about analytic functions that you haven't learned yet. So if you take a second course, you could do this thing in the first week of the class, basically. So let's see, why would that be the case? So G is another map that goes in this way. And so if I wanted to get a map to the unit from the unit disk to itself, so here's the Y. If I take G composed with F inverse, that would map the unit disk to itself and fix the origin. Okay, so Schwarz part B would imply the derivative of that is less than or equal to 1. That's right, capital F of Z equals G of F inverse of Z. Schwarz part B would imply that F prime of 0 is less than or equal to 1. And that would imply exactly the inequality I want when you do the chain rule. So the strategy for constructing a Riemann map. Cooking up a Riemann map. By the way, this map would be called a Riemann map, the F. A one-to-one analytic function that does this is the Riemann map for omega at A. And so the strategy for cooking that up is you just try to find an analytic function that maximizes that derivative. So find the analytic function G that maps omega into the unit disk that's analytic and maximizes that derivative. And then it's not terribly hard. You have to use the Schwarz lemma again. But it's not terribly hard to show that G is one-to-one and onto and does exactly what the Riemann map is meant to do. So the amazing thing is it all works. And it's kind of a fun thing to prove. Any last-minute questions about anything? Let's see. Is there a residue theorem problem due tonight that involves 1 over z cubed plus 1?
1 over z squared plus 1 squared.
Yeah.
Oh, squared. So here's some, since you came to class today and stayed to the bitter end, here's a homework hint. So you say it's z to the alpha over x squared plus z squared plus 1 to the what? Squared.
Where alpha is from -1 to 3 sans 1.
Okay, so z to the alpha would be some branch of the e to the alpha, some branch of log that you have to think about. of z. So it's just an analytic function. Is this in the upper half plane?
Yes. From 0 to infinity. So
From 0 to infinity. Oh, and there's two. Yeah, okay. So you do the Pac-Man. This would be log 0, taking the Pac-Man cut. But so you got to think about the residue of this thing at, say, plus or minus I. And so that's equal to z to the alpha over, when you factor it, z minus I times z plus I squared. And let's say I wanted to calculate the residue at z minus I. There's that formula in the book, which I detest, about a limit. And it's kind of a tricky limit to calculate usually because it's kind of like doing L'Hopital's rule multiple times, especially when there's a higher order involved, like this one. But if I just factor out z minus I squared, what's left here is an analytic function at I. Okay, that's an analytic function. Let's call it, how about h of z? And that h of z would have a power series expansion about z equal I plus a1 times z minus I plus, etc. And it's nice and analytic at I. And so when I expand that and distribute through, I would get a naught over z minus I squared. And here's the residue term, a1 over z minus I. And the rest would be regular power series. So that's the Laurent expansion for that thing. And I can read off from looking at it that that's the residue term. So the residue at that spot, the residue at I of z to the alpha over z squared plus 1 squared is equal to a1. And that's an easy thing to calculate. That's h prime at I divided by 1 factorial. That's the Taylor coefficient of that h function, which is perfectly nice and analytic at I. And so then you'd use the quotient rule for differentiating that and stick in I, and that's all there is to it. That's my preferred way of doing it. Oh, yeah?
I did have one question. So there was like removed from the bounds for alpha, there was 1. But if you do just use like the, I guess, 0 branch, at least what I saw was that there would be like, I guess, a problem anytime that alpha was like an integer, which then for me also
Is that why they ruled out that 1?
Well, so 1 is disqualified because it produces the singularity in the denominator of.
Well, alpha would be 1. That would be okay.
So it gives a different result than, like, I think it ends up being like 1/2 or something. But the integral.
If I had more time to talk about this problem, I would prefer to do this problem using the contour, this one. But then you'd have to calculate, kind of like I did, there'd only be 1 pole instead of 2, and you'd have to relate the integral along the left-hand side to the integral. You'd want the integral around the right-hand side. And you could take a branch cut going down like that. And then, but you have to figure out, this would be L1 and L2, and L1 integral would be highly related to the integral you want. That's another way to